Hi everyone, this is Tracy Smith from Finding Physics. Today I'm going to talk to you about analyzing units in an equation. So what we're going to do is we're going to look at a whole bunch of physics equations today, and I don't want you to be overwhelmed. We're not going over this whole list, and you probably can't read all of that. But we're going to look at various equations and show that the left side of the equations, the units that you have, will be equivalent to what the units are on the right. That's how we know that the equation is a valid equation, that we have the right units when we're solving. So we'll be taking a couple equations from here, and I do have the PDF of this that I can give to you so you can kind of take a look at these and maybe do more practice on your own afterwards. And we're going to identify the units of each variable that's in the equation. And then we're going to look and say, okay, look, hey, the units on the left-hand side of the equation are the same as the units on the right hand of the equation. They have to be equal. I've often used this in the past to help me when I was supposed to have an equation memorized and I thought I had the equation right, but I wasn't sure. I checked to make sure that my units made sense. As a teacher in the past, I've also given students random made-up equations and said, hey, does this equation make sense? Is this even possible to be valid? And they had to take a look at the units on the left-hand side of the equation and the right-hand side of the equation and see if they were equivalent. Because if they weren't, there's no way that could be a logical equation. So what I'll be doing as we go through, when I'm talking about units here and for the rest of the lessons that I do, I'm just going to be referencing the metric system or the SI system. I will not be using US customary units. So that's something to keep in mind. Metric system is what we will be using here. A couple things to warn you about. First, you want to make sure when you are doing problems that all quantities are in the same units. What do I mean? Well, if you have a bunch of masses, you need to make sure that all of those masses were measured with the same units before you start solving a problem. Or if you are measuring lengths, you want to make sure that all of those lengths were measured in the same units before you start analyzing the equation or doing calculations. So here are a couple little examples for you. If I was doing a problem and the initial velocity was given in meters per second, but the final velocity was given in centimeters per second, what would you do? Well, you can see that these two units are different, but they were both for velocity. Both of them have a length measurement divided by a time measurement. So my second little point here is that your best decision is typically to convert to make sure they're in the fundamental units. So for example, if I look over here, the final velocity was given in centimeters per second, but meters are the fundamental unit of length. So it would make sense to convert centimeters per second to meters per second so that the velocities agree. They're measured in the same units. Okay, and we're using the fundamental unit there of meters instead of centimeters. Here's another example. What if we had a problem and the velocity was given in centimeters per second and the acceleration was given in meters per second squared? Now, your first gut reaction might be, well, they're two different things, velocity and acceleration. Does it matter? The thing we have to look at, though, is velocity is made up of, in the numerator, it has a distance unit, in the denominator, a time, where acceleration in the numerator, we have distance, and then in the denominator, we have a time squared. So my concern is here is that in the velocity, the distance portion is in centimeters, where in acceleration, the distance portion is in meters. And that's a problem. We need them to be the same. So I would go ahead and convert centimeters per second to meters per second so that both quantities would have meters in them instead of 1 centimeters and the other meters. And this is why, guys, my last lesson where I was talking about converting, it's important to understand that we need to deal with conversions. And I'll be doing more with metric conversions in the future too. So if one mass is given in grams and another mass is given in kilograms, what would you do? We need to stop first and think, what is the fundamental unit of mass? The fundamental unit of mass is kilograms, which a lot of people forget and think that it's grams. It is kilograms. So what I would do is I would convert the gram measurement into kilograms before I start my problem. So those are a couple things to keep in mind as we go through and you start your actual problem solving. But I have a few examples here on how equations should balance with units on the left and right hand side. One thing I want to point out is that I'm not doing a calculation here. I'm merely looking at units. And in order to do this, I need to know what the units are for each of these variables. Some of the units you should know first day of school. Other ones, you'll figure them out as time goes by, so no panicking here. The first one I want to talk about is this delta x variable that you see in the equation. I spoke before about how this triangle, it's the Greek letter delta, means change in, and x is position. So this is saying change in position. We also use the term displacement for this. But since we're looking at a length, change in position, displacement, the units that we would be dealing with are the fundamental units of length, which are meters. And then in the denominator, there is a delta t. Okay, that means change in time. And we already know that the fundamental unit of time is seconds. Now, we do have this other variable, v, with a little avg next to it. This is standing for average velocity. Now, you may not know what the units for velocity are, but early on in your physics class, you're going to figure out that velocity is typically measured in meters per second. Okay, so what do I think you should know right away? I think you should know that delta x, displacement or change in position, is measured in meters because it's a length. And I think you should know that time is measured in seconds. Those are the fundamental units for length and time. Do you need to know that velocity is meters per second? You may not need to know that on the first day of school, but it's going to come up pretty quickly afterwards. So something worth noting that velocity is a length measurement over a time measurement. So let's go to our equation. On the left-hand side, we have velocity. So I'm going to show that the units on the left-hand side are meters per second. And now I'm going to look at the right-hand side and see if they're equivalent. So in the numerator, I had delta x, which is measured in meters. In the denominator, I have delta t, which is in time. And lo and behold, the units on either side of the equations do balance. They're equivalent. So I know that this equation is a good equation. It's logical because the units match up and make sense. Let's take a look at this next equation. I have VF standing for final velocity. That would be in meters per second. Like I said, velocity is in meters per second. I have VI. This is another velocity. It's just initial velocity, also measured in meters per second. The A here may be a new term for you. That's acceleration. Now, I know that acceleration is in meters per second squared. Okay, and then the last variable in this equation is the t, which we already said stands for time. So I told you should definitely know time. Velocity being measured in meters per second and acceleration in meters per second squared, they show up very early in a physics class. So they are ones worth getting familiar with quickly. But again, day one, you don't need to know that, and it's going to come up and you'll catch on to it. But let's use these units and see if the left-hand side of the equation is equivalent to the right-hand side. So on the left, I already said that's meters per second for final velocity. On the right, I have VI, so that's meters per second, plus the acceleration units, which are meters per second squared, and that's times seconds because we have times time, so that's times seconds. Now, some people, when they have a fraction, they like writing the other units of fractions. It's up to you. If you want to call that seconds over 1, if that makes it easier for your eyes to look at this, do it. Otherwise, just write it as seconds. So what I need to do, looking at this, it may not be obvious that what's on the left is equal to what's on the right. So I need to combine the variables on the right. So let's start here by taking a look at this chunk that has 2 units being multiplied together. Can that be simplified? Yes. There is a second in the numerator and 2 seconds in the denominator. So one of the numerator seconds will get rid of one of the seconds in the denominator. So now what I can do is I can simplify that quantity there to the right, those units to the right. So here I go. I'm going to rewrite this whole line, which sometimes you're like, oh my gosh, I have to rewrite this whole thing again. Yeah, when we're starting, we want to show all of our steps and make it clear to the reader what's happening here. So now when I combined what happened in green, that just simplifies to be a meter per second. Now you may look at the right-hand side of that equation and say, hey, how can meter per second plus meter per second give me a meter per second? Remember, we're not adding numbers here. We're simply looking at the units. So that's like saying, if I had one apple and I added another apple, wouldn't my answer just be how many apples? The units are just apples. The same thing here. If I take a look at what I have to the right-hand side and I'm looking, I have a meter per second plus a meter per second. Well, that answer on the right-hand side would just be in meters per second. So then I would write it one more time. I have meters per second on the left, and then my whatever I'm doing here when I add these two, I would have meters per second on the right. And you can see they're equivalent. Hey, something to note and be careful of, you can't add things unless they have the same units. Just like you couldn't add an apple and a banana and say that together it's an apple, two apples, or two bananas, or an apple banana, or something weird like that. So you have to make sure when you're adding chunks from an equation that those units are the same thing, so you can do the addition. Okay. Let's take a look at this one. We have another A here. So that's another acceleration, but this A has a little C next to it. That's centripetal acceleration. Regardless, it's still measured in meters per second squared, like the acceleration on the previous screen. I have a V, that's standing for velocity again. And we've already talked about the units for velocity are meters per second. In the denominator, I have an R. Now, maybe you don't know what R stands for. R here is standing for radius or radial length. And so since it's a length, it would be measured in meters. I wouldn't expect you to know what R means. But as you go through and you're dealing with centripetal acceleration, then you would have to know what R means. So here we go. Those are the units used for those variables. So let's go to the equation and see if everything balances out here. On the left-hand side, we have acceleration. So I have meters per second squared. Got it. On the right-hand side, I have velocity squared. So that means in the numerator, I have meters per second, and that unit needs to be squared, divided by the R, and that is just measured in meters. Now, here's an interesting thing to point out. I'm taking a fraction and dividing it by something. A lot of people think it's easier to visualize this as a fraction divided by a fraction. If you're one of those people, then just down here, just put meters over 1. It's the same thing as just meters. Now, we have to show that what's on the left is equivalent to what's on the right. All right. I'm going to first, before I do anything else, I'm going to take care of this square. I need to distribute that square to both the meter and the second that's in there. So let me do that first with a rewrite. And I think just for space, I'm going to write that over to the right here. So that's going to be meters squared divided by seconds squared. And that's in my numerator. Divided by, the denominator is still just meters, or meters over 1. Now, how do I do this mathematically? I know you were taught this some point and you may have forgotten. Some students that I've had in class, they say keep, switch, flip. The idea is this. If you are dividing fractions, it's the same as multiplying by that reciprocal, by flipping that fraction over, if you want to think of it that way. So I'm going to rewrite this line. I still know the acceleration is meters per second squared. That's the left-hand side of my equation. The right-hand side of my equation, I'm rewriting this chunk. Instead of having it as division, I'm rewriting it as multiplication. So I have meters squared divided by seconds squared. That's my numerator up here. Instead of doing divided by, I'm going to say multiplied by, and I'm going to take this meter, and instead of being meters over 1, I am going to flip that, take the reciprocal, and make it 1 over meters. Okay? That is a sound mathematical thing that we just did there. Instead of dividing the fractions, we multiplied and then flipped that over, did the inverse of that. Now, can I simplify that? I sure can. Look, I have a meter squared in the numerator and a meter in the denominator. So this meter in the denominator will cancel out one of the meters in the numerator. And now I can simplify what I have there on the right. So one last time, I have meters per second squared on the left equals, now on the right, in the numerator, I only have meter. And in the denominator, I have only second squared now. And they indeed cancel each other out. So now they balance since those m's had the cancel out there. So we have meters per second squared on the left equals meters per second squared on the right, and all is good. One last equation here, folks. So we have a new variable, but let's look at the variables we know. M is a variable that stands for mass. Mass is measured in kilograms. It's one of the fundamental units. We've talked already a lot about how velocity is measured in meters per second. And then we have this new variable, KE. KE stands for kinetic energy. And the units for kinetic energy, again, I wouldn't expect you to know this now, but the units for kinetic energy are known as joules. Now, you may stop and think, hey, I remember you talking about those 7 fundamental units, and joules were not one of them. You would be correct. A joule is not a fundamental unit. A joule is actually a combination of fundamental units. Let me show you down here. A joule is the same as a kilogram times a meter squared divided by second squared. That's what a joule is equal to. We call the joule a derived unit. So instead of every time I do an energy calculation to write the units as kilograms times meter squared per second squared, kilograms times meter squared per second squared, that can get old and it's a lot of stuff. And because it's a common clumping of fundamental units, instead it was decided to call that clumping a joule. And that's what we have, joules as the units for energy. So now let's take a look at this equation here to the right and see if the units on either side balance. I'm going to start off just saying the kinetic energy is measured in joules just to start. So we know that's the unit joules. Equals. Now the 1/2 is a constant. It doesn't have units. So when I'm doing a unit analysis, I don't have to worry about the 1/2. The M, the units for mass, we already said are kilograms. And the units for velocity are meters per second. But that meter per second is squared. Okay, so that means I need to square everything that the velocity units are. So the meter needs to be squared and the second needs to be squared. Now looking at this, I can't tell if the stuff on the left is equal to the stuff on the right because of that joule. So instead of keeping it as a J for joule, I am going to replace it with its fundamental units that I mentioned down here so I can see that the left and right hand side of the equation are the same. So on the left, I'm replacing the J by kilogram times meter squared per second squared. Okay, because that is equivalent to a joule. We said that over here by definition. And that equals a kilogram times, now I have to distribute that square. So my meter gets squared and my second gets squared. And take a look. They're the same. Both sides of the equation work out to be the same thing. The equation here is we're seeing that the units on both sides are equal. It's a logical equation, and we can see that the units are working out properly. When will I need to use this concept in class? You are going to need to analyze units and equations every time you do a calculation. It's almost every day. So you need to realize what units you have. You need to make sure that everything that's measured in length is using the same units. So there's this agreeing, and it just takes a little practice. It also takes a little bit of time and attention to detail. I know a lot of times you're trying to get through things quickly. You need to make sure you're paying attention to these little details because they do make a big difference. So what would be covered in the Finding Physics workshop? Lots of practice, taking a look at equations and seeing if the units balance out on either side. And then we'll also be discussing other derived units, like how I talked about a joule being a derived unit. We'll talk about some other ones that you might see just to get you a little bit familiar, just a little exposure. And we'll be doing a little more challenging problems with dimensional analysis prior to being able to analyze your units. That's what the workshop will include. So if you want to sign up for the workshop, stop by findphysics.com to sign up, or you could schedule a tutoring session, either a private session or get some of your friends together, a small group session. I also have on the website other tips on my blog. You can look at the podcast, the Finding Physics podcast, for some inspiration, a little bit of motivation. And I hope that this was helpful for you folks and that you can continue your journey on finding physics. Have a great day.